So in this video we're going to be looking at what happens when we send this little signal from the textbook number 4.17 through a low-pass filter. So um, as a reminder, this signal has a period of 8, so the fundamental is 1/8 hertz. And one of the other videos we figured out what the Fourier series coefficients are. So A0 is 0, the B terms are all 0 because it's an even function. And then we calculated the A terms as 4 over pi n times sine of pi times n over 4, and that's for odd n. So let's just see what happens when we send that through a low-pass filter. And that filter has a cutoff frequency of 1/4 hertz. So we know from taking 305 and from seeing this before that we have a transfer function for that circuit that looks something like that. We can rewrite that in terms of frequency instead of omega in terms of hertz, and 1 plus j over f over fc. And what else? So in the case of a Fourier series, right, we're not interested in all frequencies, just integer multiples of the fundamental. So we can rewrite this as 1 over 1 plus j n. The fundamental is 1/8, and the cutoff frequency is 1/4. So this is 1 over 1 plus j n over 2. And so if we want to know what happens as this goes through the system, we just have to look and see what the amplitude of each of our cosine waves does. So for the output, the output is just going to be an at the input times h and f naught. And in this particular case, we just plug in 4 over pi times n sine pi times n over 4 times 1 over 1 plus j n over 2. And again, just for odd terms of n. We might want to turn this into magnitude and phase terms. We might want to just go ahead and plug this into a calculator or MATLAB. That's what I did. I just looked at the fundamental and then two harmonics, and then I looked at the input and the output terms. So for the input, putting in n equals 1, you get an amplitude of 0.9 for that cosine. For 3 times f naught, or 3/8 of a hertz, you get 0.3 as an amplitude. And for n equals 5, right, which would be 5/8 of a hertz, you get minus 0.180. After going through the system, so calculating this whole term here, we end up with 0.800 at an angle of minus 26.6 degrees, 0.167 at an angle of minus 56.3 degrees, 0.067 at an angle of 111.8 degrees. So what do each of these represent? Well, remember, this is a cosine at 1/8 of a hertz, and that's going to have it's going to be the same cosine at 1/8 of a hertz on the output with a smaller amplitude. So the amplitude goes from 0.9 to 0.8, and then there's also a phase shift introduced, minus 26.6 degrees. And of course, our actual signal at the output is the sum of an infinite number of these cosines, just like our input is the sum of an infinite number of these cosines, but we've just calculated for the first few. I went ahead in MATLAB just so we can see what it looks like and plotted out for 35 terms. You can see the input, and you can see we still have that ripple that's happening here with some of that Gibbs ringing that we've talked about. And then here on the output we see the result. It's a low-pass filter, and so our system is unable to pass these areas where we have rapid changes in slope. And so instead of having a sharp change in amplitude here, for example at -1, it slowly ramps up. and then at -1, same thing. It slowly, exponentially comes down.